Welcome to the video lecture series on communication theory and techniques. In today's lecture, we will see interpolation formula. Before we go for the interpolation formula, quickly go through the time domain analysis of the signal. Here, g of t is a message signal. We multiply with a train of impulses and we obtain a discrete signal in the time domain. The time domain expression for the sampling is already discussed in the first lecture, where g delta of t is a discrete signal, which is g of t multiplied with s delta of t. When we take s delta of t, it is given by delta of t minus nts. Later, we substitute g delta of t as g of t delta of t minus nts. Then, using the shifting property, we express g of t delta of t minus nts as g of nts and delta of t minus nts. So the final expression for g delta of t, which is a discrete signal in the time domain, is given by g of nts delta of t minus nts. And when we take the frequency domain representation of the signal, we obtain g delta of f as g of f fs delta of f minus nfs, where n is ranging from minus infinity to plus infinity. And the final expression for the sampling in the frequency domain is given by g delta of f fs g of f minus nfs. Till here I have already covered in my first lecture. Now we need to see how to represent this signal in the frequency domain. The frequency domain representation of the above equation is given if you have a message signal, and if you take the Fourier transform of the g for g of t, you will get the frequency domain representation, that is a message signal in the frequency domain ranging from minus w hertz to plus w hertz. Now this signal, if you sample at a rate fs is equals to 2w, you will get the spectrum. We have already seen these criteria in the Nyquist. Next, what we should be doing in the interpolation formula is, once I have my sampled signal, now I need to able to get back my original message signal. So to do that, I need to pass my sampled signal through the low pass filter such that I will be able to recover my original message signal. So when I pass this sampled signal through the low pass filter, it eliminates all the high frequency components. So to do that, we need to again refer this equation where g delta of f is fs g of f minus nfs. Now to get back our original message signal, which is in the time domain, we need to make use of the frequency domain signal and take the inverse Fourier transform for the equation. So first what we need to do is, we need to substitute n is equals to 0, n is equals to minus infinity to plus infinity, and expand this equation. So when I expand this equation, I get fs g of f plus fs n is equals to minus infinity to plus infinity g of f minus n times fs. Here I have substituted n is equals to 0, that's why I have got fs g of f plus this component. Now the question may arise, why I need to substitute n is equals to 0. Remember, if you don't substitute n is equals to 0, you will get an expression in this form, which is ranging from minus infinity to plus infinity, and you will have all the high frequency components. But now you have to recover your original message signal. That's why you need g of f. So if you get g of f, from this g of f you can obtain g of t by taking the inverse Fourier transform. So taking the n is equals to 0, we get this expression plus minus infinity to plus infinity g of f minus nfs. This term indicates all the high frequency components which can be eliminated through the low pass filter. Next, once I pass this through the low pass filter, I'll be left with g delta of f fs g of f. See here, this expression has been completely eliminated, which is high frequency term, through the low pass filter. Next, what I need is, I need g of f. So g of f is given by 1 by fs g delta of f. Why I need g of f? Because I need to recover original message signal g of t in the time domain. Now only getting g of f is not going to be sufficient to obtain the expression for the interpolation formula. We also should know what is g delta of f. And here if you observe, fs is given as 2w. So in the equation when we derive the interpolation formula, we need to substitute fs is equals to 2w, that is twice the highest message signal frequency. Here what we are considering is an ideal sampling condition. So g of f is obtained. If I take the inverse Fourier transform, I will get g of t. I know what is fs, which is 2w, which I have substituted in my expression. But the next question comes, do I know what is g delta of f? So for that, I need to refer my time domain analysis where I have g delta of NTS. You can see here in the time domain analysis we have seen g delta of t is g of NTS delta of t minus NTS. But now I want g delta of f, for which I'll take the Fourier transform, and when I take the Fourier transform for this expression, I will get g of NTS delta of t minus NTS. If you take the Fourier transform, you will get a shifted signal, which is e to the power minus j2 pi f ts. So the expression for g delta of f is summation n is equals to minus infinity to plus infinity g of NTS e to the power minus j2 pi f n times ts. So we got g of f, we got g delta of f. Next we will substitute this in the g of f expression. So g of f is given by 1 by fs, and fs is 2 times w. Summation n is equals to minus infinity to plus infinity. Substitute this over here. Here you can see ts is 1 by fs, and 1 by fs is given as 2 times of w. Later, similarly here also you substitute ts is equals to 1 by fs, and fs is 2 times of w. When you do that, the numerator and the denominator, which has a component 2, will get cancelled, and you will be left with the expression g of f 1 by 2w summation n is equals to minus infinity to plus infinity g of n by 2w e to the power minus j pi f nf by w. Now you got the expression for g of f. Now to derive the interpolation formula, we need to take the inverse Fourier transform of this equation and obtain the reconstructed signal. Let's see how to do that. So to get the expression for g of t, as I told you, take the inverse Fourier transform for the g of f expression. So the inverse Fourier transform expression is given as g of f e to the power j2 pi f t with respect to df, ranging from minus infinity to plus infinity. This is the general expression for inverse Fourier transform. Now I need to get back my original message signal. See here, the reconstruction of the signal from its sample, it is also called as interpolation formula. So the basic technique over here is you are trying to get back your message signal g of t. But when we sample the signal, we have a frequency domain representation. So you can see all the expression what we have represented in the frequency domain. But we need to get the original message signal in the time domain. So we take the inverse Fourier transform for the signal. So getting back the original message signal from the sampled signal is what we call as a reconstruction of the signal. So to move further, consider the interpolation formula, substitute that. Now we know that our original message signal is having a lowest frequency, that is the highest message signal frequency is w hertz, and when we need to get back our original message signal, we need to pass the sampled signal through the low pass filter, which has a cutoff frequency from minus w hertz to plus w hertz. That's why we need to change the limits from minus infinity to plus infinity. If you take minus infinity to plus infinity, it means you are allowing the entire signal to pass it through the low pass filter, which is not possible. That's why you have to get only the message signal, and the only message signal here is the g of t, which is having the highest message signal frequency w hertz. That's why the limits will also change from minus w hertz to plus w hertz. If you set the limits from minus 2w to plus 2w, you will get the signal which is having highest message signal frequency, and that signal is not the original message signal. So the original message signal is ranging from minus w hertz to plus w hertz. So please see here, you can see that this is my frequency domain representation of the sampled signal. Now I need to get back my original message signal. So I need to pass this through the low pass filter, which is ranging from -W Hertz to +W Hertz. So when I pass this signal through the low pass filter, I will be able to recover my original message signal, and the highest message signal frequency is W Hertz. That's the reason in the interpolation formula, the limits will be changing from -infinity to +infinity to -W Hertz to +W Hertz. This is a very important step in the derivation. That's why G of t is -W to +W. Fs, 1 by Fs is 2W. Summation n is equals to -infinity to +infinity G of n by 2W e to the power -j pi n f by W into e to the power j2 pi f t. Next, we will see here G of t is again kept, this expression is kept as it is. Summation term we have as it is. G of n by 2W as it is. Here you can see this is an exponential term, this is an exponential term. So we take the common terms from there, where j2 pi f is taken common. When I take j2 pi f, t remains from this term, and n by 2W, there is no 2 in this, that's why we have divided by 2W. So next thing is we need to integrate this. So again, in the next step, G of t, G of n by 2W, 1 by 2W kept as it is. I integrate my exponential term. So e to the power j theta expression, when we integrate, we get e to the power j theta divided by j theta. So in the next step, we will see that G of t, n is equals to -infinity to +infinity. This term is kept as it is. We are going to integrate e to the power j theta. So you can see here e to the power af with respect to df. If you integrate, you will get e to the power af divided by a. Similarly, when I integrate this, e to the power j2 pi f t minus n by 2w divided by j2 pi f t by n by 2w. Next step is I have to substitute the limits w and minus w over here. So when I substitute in the f position, so I will get e to the power j2 pi w t minus n by 2w minus e to the power minus j2 pi w t minus n by 2w divided by j2 pi n by t minus n by 2w. So this term, if you observe, it is in the form of e to the power j theta minus e to the power minus j theta divided by j theta, which we know it is a sin theta. One thing you can observe here, this term is not changing throughout the derivation. So the only term which keeps on changing is the exponential. So first you integrate that and substitute the limit and get in the form of sine. So later when we get in the form of sine, we can see here we have sine 2 pi w t minus n by 2w pi t minus n by 2w. So eliminate the common terms. So when we eliminate the common terms, the final expression for us is sine pi 2wt minus n divided by pi 2wt minus n. So if you observe this expression, it is in the form of sine pi x divided by pi x. Sine pi x divided by pi x is sinc x. So the x term over here is 2wt minus n. That's why my final expression is given by G of t summation n is equals to -infinity to +infinity G of n by 2w sinc 2wt minus n. So this is what I call as an interpolation formula, or the reconstruction of the message signal from its sampled signal. This is a very important question when it comes to semester end exam. It is repeatedly asked in the semester end exam as well as continuous internal evaluation for 7 to 8 marks. So in the next lecture, we will see the further concepts of sampling theorem, and we will see even the types of sampling and few numericals. Thank you.